Okay, so good evening. So we are, good afternoon or good evening. So we are here for Svante for his lecture about the Flajolet prize. Okay, so the Flajolet prize highlights a person who shares many characteristics, both from the scientific and human point of view with Philippe Flajolet. And now wish to give 4 instances of this fact. As for Philippe, the scientific range is very wide. For Svante, it lies from functional analysis to mathematical statistics, probabilistic combinatorics, and analysis of algorithms. In particular, Svante has made deep contribution in the study of random graphs, where he introduced, for instance, use statistics and the film decomposition. As Philippe, Svante is interested with subjects which offer both a theoretical and applied perspective. A lot of problems he deals with are inspired by practical application, even though his main interest remains in the theoretical aspects. As for Philippe, Svante thinks about, works on, tries to answer every question, every idea which pass within his reach through talks, discussion. He then acts with a maximum concentration and impressive efficiency. Then any person, including students, is warmly welcome with a problem and question. This explains the exceptional high number of his co-authors. Svante, it's up to you.
Okay, thank you, Brigitte, for this nice introduction, and thank you, Mark, for organizing this, and thank you for also the committee for inviting me to give this lecture. I'm very honored now to give a Flajolet lecture. This year's Flajolet lecture, we heard earlier today the preceding Flajolet lecture was postponed. Now I the page down. Yes. Okay. So is it possible to get rid of this? This is better. Is this? No. I was wondering this top menu. Okay, we'll leave the top menu. In any case, so said I'm very honored to be a Flajolet lecturer, but I realized also that I am the first Flajolet lecturer that has not written a joint paper with him. I, of course, met Flajolet many times during the AofA conferences in particular. I also visited him at India once, but we never worked together and wrote any paper. We also had somewhat different interests. So Philip knew many things, but I think it's correct to say that his main interest was the analysis of generating function, both new methods to do it and the applications of it to many different problems. Of course, you all know his big book with Sedgwick. Let's see now. Right. I had to use another computer, which there maybe. Yes, now I found the right one. Sorry. But while I usually prefer probabilistic methods, so we had that reason somewhat different tastes, you could say, methods. So for that reason, I've now chosen to speak today about the problem where I and my co-author, who you will hear about soon, we have had to combine both generating functions and probabilistic methods to show different parts of the results. So in brief, we use probabilistic methods to show convergence in distribution, and we use generating functions to show convergence of moments. This is so maybe Philip could have proved all our results by single method, but I can't. This is a case where I certainly find both methods very useful and their combination. So let me first say some more philosophical things here. Since I have, as I said, I usually prefer probabilistic method, because my background, I'm not going to argue why I prefer them, just the way it is, and others have different takes. And I sometimes tried and sometimes managed to reprove things that others proved using their methods, and I proved them with probabilistic methods, and that is fun, and I hope I can do it more time. But it still has to, I think it's important to stress that it has to be what I say, a friendly competition. We can engage in friendly competition with different methods for same problem, but we should also be respectful, and as I said here, a bit exaggerated maybe, that we should respect, love, and learn all methods, because different methods are useful for different problems, and it's useful to use or combine different methods, which I now hope to demonstrate in this lecture. So this lecture is mainly based on a joint paper with Jim Phil, which you can find on archives from last year, but also some things are maybe taken from some of these papers. So here's a list of some related papers. There are certainly not all of them, but some ones from, and that includes one paper by Philip together with Jim Phil and Kapoor from 2005. We are certainly using some results from that paper in an essential way. You can also note here, if you look at this list of references, that there seem to be interest in this type of problem. I haven't told you yet what the problem is, but I come to that. But it was certainly interest about 20 years ago of different versions of this problem, and then not very much happened until the last years. And it's actually the same thing with our paper. I and Jim Phil started this research about 20 years ago. More precisely, I found an email where we had sent the first result we approved, which now is part of paper from 2003. And we did some work, and we also wrote some other related paper, but for some reason we never completed this one. And it wasn't until recently, in last years, we dug this up again and had the energy to complete it. So I hope it has got a much better meanwhile now during this long wait. But now at least it is here. So the general problem I talk about is about additive function. It would be a special one, but let me first say the general one. We have here function, we have a tree, a random tree, of course it will be there, and we have a additive function defined by a toll function. So now let me draw a piece of blackboard. If you look on the screen instead. So we have a tree, which you should think of as a random tree, and it's a rooted tree, so we have a root here, and by definition a fringe tree is obtained by taking any vertex, this one for example, and we take all its descendants, so everything that's above it, or below it if you draw the tree in the opposite direction, away from the root. And you, of course, this is a standard thing, but I want to remind you that it's always very misleading when we draw pictures with tree by hand, because they are very small. We of course are interested in asymptotic, very large trees, and then it's important to note that almost all nodes lie very close to boundary. They may look like this. We have very many nodes here. Typically, we have some fixed proportion of the nodes are leaf, for example. So if you take a fringe tree here, just a single vertex, and another large proportion is maybe like this, you get a vertex with say 2 children or 1 child and so on. So fringe trees are typically very small, but of course they are big ones. If you happen to start at the root, the fringe tree will be the whole tree. So that happens, but not very often. So what we do, we take some functional, and what I'm going to do is a special one, so we can do that immediately. So I just take the power of the size of the fringe group. So in other words, my functional here, f alpha of t is I sum, well, okay, it will be on next slide. I sum the size of the fringe tree at vertex v raised to power alpha. As I said here, typical problem study asymptotics now, distribution of mean and variance and so on, for some random tree. Many people have done looked at various aspects of this problem, more or less in generality. So what I'm going to do here today is to talk about this specific case, which we analyze in great detail. And the random trees I'm interested in today are the condition Walton-Watson trees. We have heard about them earlier today. So let me just remind you that we get them by taking a Walton-Watson branching process. So we start with the root. We have a number of children, which is random, given by some given offspring distribution. And then each new vertex gets its own children by the same distribution. Everything is independent, but it's the important thing. We then condition the whole tree on having a given large number n of vertices, which of course makes this number of children dependent a bit. So we also do a standard assumption that the mean of this offspring distribution is 1. That is more or less a normalization thing. And we also use my standard favorite assumption that it has finite variance, non-zero to all trivial case. As you know, there are also interesting cases where we have infinite variance, and one typically get different types of limit results. And I'm sure that one can get results similar to ones I'm giving today, but they will be different if we have infinite variance. Let me also comment, since that's one of my favorite technical details, I like to stress that this setting, of course, very standard one with condition Walton-Watson trees, and we almost all know that this is essentially the same as looking at simply generated trees. Just the formalism is a bit different, but they are, in most cases, are equivalent. But there is a somewhat psychological difference that in the formulation with simply generated trees, one typically uses generating functions, and then it's very natural to assume that you have a certain critical point inside the radius of convergence of generating function and so on. If we translate that into these probabilistic terms, it means precisely that this offspring distribution has not only finite variance, but actually it has some finite exponential moment, which, as I said, seems to be a very natural condition from the point of view of generating function if you look at it from that perspective. But if you look at it from probabilistic perspective, it is a quite strong assumption, and this assumption of finite variance seems more naturally weaker. So that is one. Now, of course, if you know that, you can also use this assumption when working with generating function, but it's one example that different methods may lead you to assume different things, because they may be more or less natural in the methods, even if they are not really needed. In any case, this is what I'm going to talk about later, condition Walton-Watson trees with some fixed offspring distribution having this property, and I will with a few exceptions, not assume anything more about this distribution. We all know that there are lots of standard examples of combinatorial trees, like uniformly labeled trees, for example, which are of this type. So there are interesting examples. And we studied this functional f of alpha. And I just gave 2 standard examples that we all probably heard of. If alpha is 1, we sum the sizes, we can rewrite the sum and see that it's same as the total path length, which has been studied a lot. If we take alpha equal to 2, so we sum the squares of sizes, we get a function which has appeared in the study of the Wiener index, which I will not say anything more about, because if you don't already know, you will not be interested today. But the important thing today is that I will allow this alpha to be complex. That is, I think, a novelty for this problem. So we will regard this f alpha as a function not only of the tree T random tree, but it will be a function of this complex variable alpha. And I also use this simplified notation. Xn of alpha is this sum I have here for the tree Tm, which I said is a random tree of size n. And Xn tilde is the same thing when I subtract the mean. So why do I want to use complex alpha? Well, there are two reasons. One is that it turns out to be useful in the proofs. Also, if I really only want to prove the result for real alpha, the method we use really uses the complex alpha, and I will show you why, since this is, I think, is maybe a novel way of looking at things. Since the powerful method of analytic functions turn out to be useful here. But then there's a second thing also, that it gives us new problems to study, which you of course like as mathematicians. So if we know everything about alpha on the real line, we can still ask question, what happens with phase transition in the complex plane, for example? And I will give you partial answers to that. So I said phase transitions, and this is, I think, more or less known since these papers 20 years ago, that there are two phase transitions now for real alpha. Alpha equal to 0 and alpha equal to a half. And I'll soon show you in what ways they are phase transition. They are phase transition in different ways, I would say. So that means that at least it's natural to look at these three phases in the complex plane when the real part is below 0, between 0 and a half, or above a half. And I will give you a main result for these three cases and show the differences. So then it's a natural question now, what happens at the boundaries when the real part of alpha is 0 or the real part is a half? There I can comment immediately that if you still are a bit old-fashioned and only want to look at real alpha, then the case alpha equal to 0 is not interesting, because if you remember the formula, if you put an alpha equal to 0, you get just a constant answer. Alpha equal to half, on the other hand, is an honest, interesting function. So you can ask what happens precisely when alpha is a half, and we'll see that later. Okay, so here is the first. Here's the theorem. You don't have to do all the details, but I want to show you what happens on the first phase here, when alpha is less than the real part of alpha is less than 0. So let me try to draw a complex plane here. This is complex plane, and here, so this is alpha in the complex plane. So now this is, you can say, case 1, where the real part is less than 0. There it turns out that the limit is Gaussian. It's Gaussian limit. I stated now to stress the fact that we're looking at functions alpha, said that this random function xn tilde alpha. So remember, I said we think of this as a function of alpha. So for each realization, we would take our random tree T, and then we make this sum over all alphas. That gives us a random function of alpha, which and xn tilde means, as I said, we have subtracted the mean, whatever that is. And if we now divide by square root of n, it will converge to some x tilde alpha in distribution. And that x tilde alpha is a complex Gaussian variable. So complex Gaussian, that means that the real and imaginary parts are jointly Gaussian variables. So if we identify a complex plane with R2, it is just a two-dimensional Gaussian vector. I don't assume anything special about the relation between a real and imaginary part. They may have different variances, and they can have any kind of covariance and so on. So for each fixed alpha, we have a complex distribution, and of course jointly also. On the other hand, the covariance matrix here, it depends on the offspring distribution, which I fixed from the beginning. So this means, say this because contrast what comes later. So the reason you can say intuitive for this is that, as I said, the fringe trees, most of the fringe trees are very small. So we have very many very small fringe trees, and we have a few large ones, and of course some intermediate ones as well. And in this range, when alpha is small, that means that this power is dominated by the fringe trees which are small, with many of them, so we have a sum of very many parts which are essentially independent. Fringe trees at different parts are more or less almost independent. So it's not surprising that in that case we get the Gaussian limit, and we have the usual square root of m type of normalization. On the other hand, for the same reason, this is dominated by small fringe trees, and the small fringe trees, the number of them, so depends on the details of this offspring distribution, as it's well known and easy to see. Therefore, as I said, we get covariance matrix limit distribution, which depends on really the choice of the offspring distribution. So we have normality, but not the universality in a stronger sense. As a contrast, let's look at the next case if the real part is bigger than 0. So here is real part alpha is bigger than 0, and let's put alpha half here. This version here, we don't see any phase transition at a half. That will come later. So this is now valid in the whole region here. Here we need a different normalization, n2 minus alpha minus a half. So if alpha is positive, a real part is, that means we have some divide by a larger thing. And then we get converged in distribution again to random functions. Again, we think of this as a random function of alpha in this half plane, and it converges in distribution to something which now is not Gaussian. But on the other hand, it does not depend on the offspring distribution. So it is universal in some sense, but it's not normal. And the reason is that this sum now is dominated by the rather few, rather large fringe trees. Say the fringe trees of size order n, half n, and so on. And you can, one can easily see that there are roughly root n of them, and each of them give a contribution of order n to the alpha here, and somehow explains this normalization.
Svante, can you hear me?
So we have two different types of behavior, which explain by fact whether small or large fringe trees that really dominate this sum here. And I should also say here in both of these results, we have, as I've written, I didn't say, we have convergence in distribution, not just as each single alpha or a finite number of them, but actually convergence in the space of analytic functions in the respective half space. And this space of all analytic function half space, we use the standard topology, which is convergence, a uniform convergence on compact subsets, which is a very nice topology for several reasons. So you can think of this as converging uniformly with some compact subsets to some nice, interesting analytic function. Okay, so now I want to say a little bit more about the mean here. Since so far I've talked about results by subtracting mean, and now we have to introduce the mean also. So here is first a comment that take the unconditioned Goldmotzky. I mean, I said we condition on a given size, but if we don't do that, it is well known that with my assumptions, the probability that the size is n goes to 0 at this rate, n2 minus 3/2. And it is not so difficult to see, at least it's some known fact, that if we take a random fringe tree, say take a random point of fringe tree, the distribution of that will converge to this unconditioned Gorton-Watson tree. Or in other words, the number of fringe trees of size k is like, say, n times k to minus 3/2. And now I take this mu of alpha is the expectation of the size of the Walton-Watson tree raised to power alpha, which you can write, of course, as some I've written over, some I've written there with probability sizes n and n to the alpha, which converges, therefore, as you easily can check if you follow all the details are written, it converges in these half planes here. This half plane, so it's part 1 and 2. And therefore it defines an analytic function there. But it will diverge if we go beyond here because, well, because the terms will not go to 0 fast enough. Okay. So having defined that function, this you can see intuitively, it may be reasonable to take that this should be important. It turns out that it is, because if we are in this half plane up to a half, the expectation turns out to be just like n times this function mu of alpha. So you can, if you want, forget the definition of mu of alpha, just accept that there is an analytic function in this half plane, so that the mean is like n times, or mean divided by n converges to this function. Of course, again, uniform and complex sets if you want to be more technical. On the other, and intuitive again, or the formula, this is again because in this range, the mean, in this case, the mean is dominated by the small fringe trees, which are many ones close to the boundary, and there are roughly n of them of n given size. That explains why we have this factor of n, and it also explains why we get this mu of alpha. But if real part of alpha is bigger than a half, if we are on this, which I call part 3 here, then the expectation is instead like some constant, have this explicit constant depending on alpha times n to alpha plus a half. And that's because now the mean is dominated by the large fringe trees, and then it's rather easy to see that this is what you get as a leading term. So I want to point out here that there's a difference. That's why we have phase transition at a half, and we have now phase transition at 0. So this phase transition at a half is a phase transition for the mean. This is where, in this case here, the mean is dominated by the large fringe trees, but here the mean is dominated by the small fringe trees. But on the other hand, the phase transition here was for the oscillation when I had subtracted mean. So you can, so it means that in the phase in between here, the mean is dominated by the large fringe, by the small fringe trees, but the fluctuations are dominated by the large fringe trees. And that is why we get 3 different phases. So you can see if you compare these point 1 and 2. First one we have it grows linearly in n in this region here. Here it grows like n to a larger power, alpha plus a half. And so you can think of these two as 2 terms, one coming from the small fringe trees and one other from the big one. And you actually, in some range here, you can get a better approximation with smaller error term if you use the sum of these 2 terms. But I'm not going to that now. But we also see when alpha is a half in the middle here, when the 2 meet, combined with them, as we often get in similar situation, we actually get an extra log factor. That means there is like n, grows like n log n. Okay, now you can't really see top, but that's not important. It just says I defined this y tilde of alpha as the limit before of my normalized random variable where I had subtracted the mean. Now I add back the constant I had in the previous formula to get back the mean, or at least asymptotic for mean. And so as a result, that defines this random analytic function y of alpha, which is defined now in this. So y of alpha is defined for alpha bigger than 0. So y of alpha is defined here. Y of alpha is defined for real half alpha bigger than the right half plane. This is a random analytic function, and combining the previous results, we see that if we now don't bother about subtracting mean, we just take our variable x and alpha as it is. If I divide by the right power of n, it will converge to this y of alpha in phase 3 when the real part is big enough. In this part in between here, I have to subtract, well, it says real part less than half, but also it says earlier, which you can't see. So real part should be between 0 and half. Then if we subtract my approximate mean, this n times mu of alpha, and divide them by right power, it again will converge to this y of alpha. And you see, there's just a scale factor here. Sigma is the variable standard deviation of the offspring distribution. That's the only way the offspring distribution affects the result here. Right hand side. But if alpha is equal to half, when these two somehow meet, then well, this is the formula I had before. Okay, that is was a editing mistake. What I should say is that, well, again, if we have to subtract, we have to divide by the square root of n log n. So log appears again, then we get convergence to something. So this shows the three somewhat different behaviors in the three different regions. Now I want to add for moment convergence that all moments converge in these theorems when real part of alpha is bigger than 0 for all the results I said before. And the limiting moments, they are just these moments of this unknown function y to alpha. They satisfy recursion, which I write here. As you see, it's a rather complicated one. It's a quadratic recursion in this kappa, the moments. But if you know this kind of things before, if we take the special case when alpha is equal to 1, so remember that was the total path length, and then we know the limit is the Brownian Brownian excursion area, which Philippe Flajolet and others call the area distribution. Then this is actually a well-known recursion which goes back to I'm not sure really who first did in this form, but Louchard was one of the people who were using this recursion, and Philippe Flajolet also in paper, and maybe Takash was even before them. But in that case, you can see that this is kind of generalization where you put in alpha in the right places. There's a small technical thing here that for a case when alpha is equal to a half, actually we have to assume a little extra moment of offspring distribution for our proofs here. So that is something I don't think is really necessary. So it's an open problem to eliminate this small thing. But for bigger and larger alphas and complex ones, so we don't need this. Then there's another thing I just said when alpha is bigger than a half. Of course, now when I was preparing this lecture, I also looked in our paper, but I couldn't see any comments on moments in this case. So I think it's a bit embarrassing. I think that we forgot to check that case. So I'm sure that moments converge there too, in that case too, but it's not really proved yet. So how do we do this mean higher moments? Well, this is based on methods in this paper by Philippe Flajolet and Kapoor, which also looked at some simple special cases of mean, I think. And you can see that those methods are also in the book by Flajolet and Sedgwick. You can read them there. So the idea is we define some generating function. I'm not going to I've written it here for those who are interested, but we first one is standard function we deal with is Watson trees or simply generated trees, and then we put in natural generating function to study the nth moments, and b of z is where come from this toll function. Z to the z should obviously be z to the n, another type of. And then we use Adamar products, and I will not bother to say what it is. If you don't know it, you will don't want to hear it today. And we get in this rather complicated recursion formula, which gives us this generating function ML in terms of the lower ones. It is large sum over n plus 1 tuples, and it involves these Aranor products and ordinary products and some derivatives. Well, so it's not obvious, but that was point of the paper by Flajolet and others, that one can analyze such recursions by using singularity analysis, and one can find the leading terms and actually get something useful out of this. So that's how we get results for moments. Now I want to instead talk about the probabilistic approach here and how to use Brownian excursion. Because we've known that Brownian excursions are very important in the asymptotics of the Watson trees. So let E be a standard Brownian excursion. I'm not defining it, but remember that that is a random continuous function on the interval from 0 to 1. It starts at order 0, it's positive, it ends at 1 here, and it's informally it's a Brownian motion condition to start at 0 and end at 1 and be positive in between. And I make this definition now for any function on the interval 0 to 1, say, and 2 points S and T. I want to know notation for the minimum between. So this is S here, here's S, and here is T. And so this value here is M, S, T, this function G. Because here is a formula, this limit variable y alpha, we have it. If the real part is bigger than 1, so then I'm even further away here, then I can write down this explicit formula for y of alpha in terms of a Brownian excursion. So this ME is what I've done here for the random Brownian excursion. So remember, E is a random function. For each realization of E, we compute this for all values of S and T, and then we compute the double integral I've written on the slide, and you multiply it in the right way, and you get the y of alpha. So you can do this for all alpha in the half plane, and that will give you your analytic random function alpha, which is the limit in that area. And the proof of this is not so difficult, really, knowing what we know a lot of known things here. The idea is, if we, I just said this for those of you who know the thing, if we have a random tree like this, we can define the contour process, which will be a kind of, well, it's just a random, say, walk going up and down, but we know it will be a discrete approximation of this. It will converge to Brownian excursion of the proper scale. And if we instead put in the contour process in this integral, then up to a small error going to 0, we can compute this integral and see that we will get just our sum here with some scaling. And therefore, if, as I said, the contour process converges Brownian excursion, then therefore, and this integral then will converge to the integral I've written. Because it's a continuous functional in this rate. And here it's important that alpha is bigger than 1, because otherwise this integral will diverge. This t minus s to alpha minus 2 is no good if alpha is less than 1. You can take alpha equal greater than 2 to be real on the safe side, but alpha bigger than 1 is enough. There is another more complicated or similar formula which works for all if the real part of alpha is bigger than a half, for the same reason. I'm not going to details here, just point out that here we can take alpha equal to 1, and it will simply reduce to this integral here, which is the Brownian excursion area I said before, what's called the area distribution, which you may have seen before in this context. So here, the complicated formula above one in red, you can think of as a generalization of this simple formula for alpha equal to 1. So next step in the proof. So this is gives a proof of convergence now to this y of alpha in the range where real part of alpha is bigger than 1, or maybe bigger than half if you use the second formula. But we want to go all the way down to 0. And we want to prove this thing also for real part less than 0. So what we do here, we want to prove tightness. Since we want to prove convergence in the function space, space of continuous analytic functions, we want to prove tightness in usual way. This is where it's very handy to have analytic functions. So I'll try to explain why. First of all, we have a lemma where we compute some variances in standard straightforward ways, which tell us that the normalizations we had before were the right ones. If we normalize in the way we did before, the variance will be bounded as n go to infinity, and that is called uniform. Well, for each fixed alpha, but it's also uniform in the compact subsets. So that shows us that these variables now normalized in the right way. There are tight at each for each fixed alpha. Well, okay, that's good, but we know that when we are dealing with functional limit theorems, we heard some example of that earlier today in Belling's talk. Example, we have continuous functions on an interval, say, and we want to show that they convert random continuous function. Well, a typical way to show tightness is want somehow uniform continuity in this thing, up to with high probability, and one can do that in various ways, but you have to do usually a substantial amount of work to do it. But here it's a shortcut now for analytic functions. Now let's take away this and take another picture. So the idea is this, here I've written down a detailed statement. What it says, we have a sequence of random analytic functions in the domain D. Let's say this hot tank here. It doesn't matter at all. And we have these random analytic functions, and they are now normalized so that the mean of them are bounded at each point by some function which I just call gamma, and gamma is again bounded on complex subsets. So then I claim that this is enough to show that this sequence is tight in the space of analytic functions. And the reason is this, that let's take a disk, for example, any complex subset. We do take a disk. So I want to estimate analytic function yn, the derivative here, yn prime. When this is a set, let's call it A. Okay. Well, to do that, we take a bit larger circle around it or some other curve around it, and we can use the Cauchy integral formula and express the derivative at any point as some integral around this curve, and we put in absolute values and so on, and see that we have uniform bound that this is yn prime z is bounded by some constant times the integral over this curve, say gamma, of the absolute value of yn. So this is now uniform with some constant for all z, so I can take the supremum here over my set k. And now I take the expectation. So this was configured the formula. And then, as I said, expectation of integral is the integral of the expectation. I can put this inside, and I assume that I had a bound of this pointwise with z, and that gives me just a constant. And then it will expectation of supremum is bounded, and that is precisely what we need. So I want to stress here the fact that this Cauchy integral formula makes it possible to do this simple trick. We can just if we want to use functions on the interval real line, so solve a problem that we would like to, we need some bound on supremum. Maybe we know bound supremum function, for example, more or less what we want. But find the expectation of the supremum is often not so easy, because but here we can use this trick and convert it to expectation of an integral, which is just the integral of the expectation, which in this case is easy. So that was one thing. So therefore, these functions we have are tight. Next thing is another technical lemma here, which I'm not really all in, but when we now know that these functions are tight, we still want to show they converge. And then what this lemma says, if you read the details, is that if we have a tight sequence of functions, which are tight in space of analytic functions, if I know that they converge on some same interval here to make it simple, any set with a just a point with a limit point inside ID, it's a very closed infinite set in D is good enough. If I know that they happen to converge at these points, then they have to converge everywhere, also here, and in this space of analytic functions. And again, this is because of the magic of analytic functions. And the reason is that we know analytic functions are determined, in this case, by values on this small set uniquely. And therefore, since we assume they're tight, we can select subsequences that converge, and then the limit is uniquely determined what happens here, and so on. So by some general technical argument, we get this result. So if we now go back to our YMs, we now know that this thing we could do with Brown dispersion work for some large alphas. Would be enough to do it with real alpha here, for example. And together with this tightness argument, this limit tells us that the random analytic functions actually do converge to something. Okay, so now I'll end now. We'll have some few comments at the end. This was, you can say, the main results. But here are some more technical things for those of you who haven't lost track of technical details but want some more technical things. So what happens now on this line alpha equal to half? Well, now we can do this line here. This function u of alpha, I said it was an analytic function in the half space to left. It's easy to see that it will go to infinity if I approach the point a half. But it turns out that it actually extends to a continuous function as limits at all other points on this line. And actually, this formula for the expectation, asymptotic formula, also holds on this line except at point a half. But then it becomes even more tricky because it extends continuously. And it turns out if this offspring distribution has more than a second moment, it actually extends analytically a little bit longer. And so you have a pole here at the half, but everywhere else on line it extends analytically. And even if we have moments of all orders, it becomes meromorphic function in the whole plane. But in this case, we really need more moments because we could construct a complete example of an offspring distribution without any higher moments, where this function cannot be extended analytically along across this line at all. So here's a case where it really makes it's a difference if we assume higher moments or not. Another thing is the critical point of zero here. So as I said, if we just take function alpha equal to 0, we get something non-random. But the derivative at 0 is what's called the shape functional. It becomes, you take the derivative here, you see you get the sum of the logs we studied before. And in that case, we get a normal limit law in general. So remember, we have normal limits to the left of this in left half plane. So in some sense, we have a normal limit also at 0 here. And so by continuity, you would expect normal limits maybe along this line, and I'll return to that. One result we have is we do something differently. If we let first n go to infinity, so we look at our limit function, this random analytic function y of alpha in the half, right half plane. There I can show that if it goes to 0, if alpha goes to 0, it will convert to 0, not surprisingly. But actually we can rescale it. So we prove that if we divide by root alpha, we have a normal limit here with a certain variance. And but we could show that if we go different lines, you get different limits. So we still convert in distribution, but with different covariance matrices. So that's a bit complicated. And we have a conjecture. Okay, look at the theorem first. Same thing happens if we converge to some other point here. Then it will go to infinity, this function y alpha in probability at least, showing that certainly it cannot be extended to an analytic function in larger domain. But if we scale it with a real part to half, it will convert to a symplectic complex normal variable. And this conjecture, which we haven't really had time to prove yet, that we actually get convergence of these xn at the imaginary axis, but the right normalization is by root n log n. So again, we get now the log n at these interfaces. So that was a conjecture. Okay, this is more technical thing. For a Brown excursion, we had this explicit representation using Brown excursion for large alpha. So by some general abstract nonsense, you can say that somehow the limit, also in the range between 0 and half, is given by some analytic extension of this function of a Brown excursion. But we have no explicit formula. We don't know if there exists an explicit formula in any reasonable sense. So that's an open problem. And let me just finish by saying that all this was for condition Galton-Watson trees, but you can ask the same question for other type of random trees. So there are some partial results. I don't think anyone has looked at complex alphas and this type of problems in this context, but I expect similar results. But if you take, for example, binary search trees, we have a somewhat different number of fringe trees of other sizes. So phase transition should be at 1/2 and 1 instead of 0 and 1/2. But probably we have similar results, but that's open problems. Random recursive tree are even more open, less is done. Deer increasing tree is another example where I don't think that even the positions of phase transitions are known. So there are lots of open questions in all cases, and certainly you can find out, I think of other examples of random trees, which I haven't even mentioned here. So, okay, that was all. So, any questions or solutions? Or
Thank you very much, Svante. So, are there questions?
Svante, can we just see your just your face? You know, maybe I'll make it a little bigger. Okay, there we go.
good.
Yeah,
Other questions in the chat?
yeah. Oh, let's check the chat. Thank you.
Okay, I have one question here from my local audience.
Yes, sorry,
Cecilia, yes.
I was just wondering if you had thought of the case when the variance is not finite as well for the condition Janson trees.
I don't know if you heard it, but Cecilia asked if I thought about the case when the offspring distribution for my conditional Galton-Watson tree has an infinite variance. And well, the honest answer is that I have thought of it so much that I realized that that is another interesting problem, but I haven't at all tried to solve it. So that is something which also is wide open for future research.
May I make a comment? I don't know how to handle these things. Hör du mig, Svante?
Ja.
No. You had this problem at alpha equal to 1/2 when it was not possible to extend something, right?
Yes.
Analytically. And I just recall there is a paper by Carl Gustav Essén, 1965, when he wants to go from characteristic function but cannot extend beyond the imaginary axis.
Mm-hmm.
Is there something that could be stolen for you in that paper? It's in Archiv Mathematik, 1965.
I will check it. Certainly it is the same type of problem where you cannot extend it, but whether the function he looks at, characteristic function he looks at, has any direct relation to this function here, I don't know.
No, but it was a method for him to move from characteristic functions to moment generating function, in spite of the fact that it was not extendable beyond the imaginary axis. That was the problem.
Yes, okay. Now I'll see if his method can be useful here. I have no idea, but that's an interesting idea. Thank you.
Andre's asking a question. You can ask your question out loud if you want.
Okay, ask a question.
I have the mic on. Can you hear me?
Yes.
I can hear. Yes.
So first of all, thank you for your talk. That was beautiful and quite instructive. And you know that on a work we have been working on something similar, but now I wanted to mention something a bit different that we did with Sergio Caracciolo and Alan Sokal in another point of our life And that was Alan Sokal that discovered that back in the literature. In fact, there is a famous problem posed by Gelfand on the analytic continuation of certain functions, which are described. Well, the analytic continuation was in a power parameter, in a way somewhat similar here, but without randomness, just analytic continuation of deterministic functions. And the idea is that there are certain ratios of gamma functions involved, and in fact, you can analytically continue the function to the whole complex plane except for a semi-infinite sequence of points on the negative real axis. And this problem was brilliantly solved by Bernstein, who invented for the occasion, in a sense, the theory of Bernstein's autopolynomials. And this has been very instructive for us. We have been studying a bit the theory, although it's very difficult. And something that happens is that when you go beyond the natural boundary in the real part of your parameter, normally the functions that you have in your integral definition of the operand becomes not integrals of functions, but integral of Schwarz distributions, and which are obtained essentially, they are described by iterated integration by parts. I wonder if your formulas with the Brownian excursion could have an analytic continuation which is somewhat of this fashion. So the Brownian excursion is sandwiched with something else and then integrated over, and that something else, when you go towards the left part of the complex plane, at some point becomes a distribution that is defined through one integration by parts. And then if you go to a second slide, it involves two integration by parts and so on and so forth, with a Sato polynomial and something like that. So this is something that maybe we should look with more quiet, but it could be, I'm sure that there is a lot of interesting mathematics there. So possibly well, you can dig it out.
Okay, yes, well, no, I did not know this, so obviously I cannot say if this is works here too, but it is an interesting idea, and so it's quite possible that it could be, its extension could be of this type you say, that involving some kind of distribution, random distribution there, perhaps, but as I said, I certainly cannot say for anything for sure, no, but thank you for this idea. I agree, it is certainly worth looking at. I hope that you will look deeper into this.
I try to take the rust out of my memories and write an email more quietly.
Okay.
Okay.
Okay, thank you.
Okay. I think there is no more questions. So thank you very much again.